Okay, so our last section of part one is the idea of other ways to collect data besides just doing a survey, things beyond just our simple sampling methods, and that is experiments and observational studies. And we saw these a bit on Thursday with that worksheet and sort of determining which one we should use for those different examples. But again, this is something that is frequently on exams, not guaranteed, but I have put it on exams before. And the big difference between an observational study and an experiment, we do not try to influence what's happening in terms of responses in an observational study. We usually just come around and we look and see what has happened, and we try to describe what's happened. So the CT example from that worksheet was an observational study. We didn't tell people whether or not they needed to take the CT sessions. We just let that organically happen, and we observed what the result was. An experiment, on the other hand, we have to impose a treatment. So this can be asking students to go to those CT sessions, telling them that they've been randomly selected, asking someone to read or watch something, as opposed to just saying, have you read this? Have you seen this? Did you go? Instead, we are actually saying, you need to go, you've been selected. An experiment actually allows us to say a little bit more about a causal relationship than a observational study does. Because in an observational study, there's going to be a lot of selection bias. People who choose to do certain things are different than the people who don't. So our first exercise here, I'm going to give you a moment to read through and try to answer. So pause the video and take a shot at 1.6.1. All right, so the answer to 1.6.1 should have been B. If you chose A, let me show you where you got tripped up. So we were told that a group of adults who swim regularly was evaluated for depression, and it turned out that these swimmers were less likely to be depressed than the general population. In a second study, so, that crap before, that was the first study. All we did was see people who swam regularly. We didn't tell them to swim. So this was the first study, and this first study was an observational one. Then we kept going. We had a group of volunteers divided into two groups. The first was asked to swim. Here's our treatment, right? Asked to swim twice a week. The second did not follow an exercise plan. So if you chose A, chances are you got the studies confused with the groups, and you saw our treatment group and our control group, and that's why you had an experiment versus an observational study. But really, we had a first study and then a second study where we had a treatment and a control group. Our observational studies fall into one of three different types. The first type is a cross-sectional study. All of our data is collected at the same time point. So most of our surveys you can almost think of as just a cross-sectional study. We're just, what did you do? What information do we have? Retrospective studies look back in time. So a retrospective study, you find people who have lung cancer, ask them about their previous smoking habits. Retrospective studies have some really big positives here. In terms of positives, we can use them to look at rare outcomes. So something that doesn't happen very often. You can't do a cross-sectional study to study lung cancer because you'd have to take a really, 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 really large sample of people before you got a large enough number of people with lung cancer to actually make any meaningful conclusions. So it is much easier for a rare outcome or something that takes a while to develop to use a retrospective study. The biggest negative with the retrospective study, if we're asking people about the past, they're not going to remember everything, right? So we have what is called recall bias. Just means that our data is going to be imperfect because we're asking people about their past behavior and past history. Our last method here is a prospective study. This is where we follow somebody forward in time. So our example here, they took an absolute giant sample of people in the 50s who are 50 to 65 years old. They started in 1993, followed them to 2002, and we're trying to figure out how many of them came down with coronary heart disease and what things they had done that might influence that. Prospective study, the big positive for it is we're going to have great data, right? In addition to the fact that we have great data because we're able to say, oh, here's something we're interested in, let's collect it, let's have them, every year send them a survey or ask them something and just sort of see how this is progressing. We also have the ability to sort of see how things change over time and see if that's an influence. So we have really nice data, and we're able to do a lot of kind of cool analysis with data that's from a prospective study. The negative though, this obviously takes a lot of time and a lot of money. You can see here, if you're these researchers in Denmark, you started in 1993 and you had to wait 9 years before you could even analyze your data and say anything about what might have influenced whether or not someone had coronary heart disease. So it is a very, very slow and very, very expensive process. The group I worked with at UCSD falls kind of into this category. And I mean, they flew 1,200 twins to San Diego, put them through 2 days of testing with hotels and paying for MRIs and all of that. So it was a very, very costly endeavor every time they had to collect a time point. So I have a quick exercise here. If you're studying the factors that might impact a person developing brain cancer, which of the methods above would you use? So I want you to think about it for a moment. Which one really makes sense? You can pause if you want a little extra time. Otherwise, I'm going to tell you the only thing that really makes sense for this one is our retrospective study. Because brain cancer is rare, right? If brain cancer is something that doesn't happen with a large occurrence, then we'd need to take a gigantic cross-sectional survey in order to find enough people with brain cancer to have a meaningful sample size in that group. And if we were doing a prospective study, we again need to have a huge number of people and then follow them for a very long time to see if they came down with brain cancer. Since it is rare, that's going to be our big issue. So the only possible option here that really makes any sense is to do a retrospective study. All right. Our experiments, we have a number of different types of experimental designs. This is by no means a complete list. But 3 of them, which are ones that I have tested before, so I'll go ahead and put a star here, completely randomized. So we have all of our subjects, and then we randomly assign them into their treatment groups, and we look at our results. This has a feeling similar to an SRS. There's a big difference between all the experimental designs and our sampling methods, and that is an experimental design, we are assigning treatments. So our question is always, how were they assigned into the treatment group? Versus a sampling, we're figuring out who's going to be in our sample and everybody else is not left out. So here, all of these subjects we're going to get information from. It's just a question of what treatment group they're in. Versus like an SRS, when we have our population or our sampling frame, and we're not even going to get information from the people who aren't selected. So everybody gets randomly assigned here. The completely randomized has the same issues as our SRS does. Because it is completely random, which is ideal, we could still end up with something funky happening. So a way to fix that is to use a block design. So in a block design, you can take all of your subjects and then divide them by some characteristic you think might influence outcomes like gender, and then do your random assignment from those gender groups. So that way you have an equal number of men and women in both your treatment and your control. So I want you to take a minute and think about which sampling method this reminds you of, because it definitely should remind you of a stratified sample. Again, it is not the same as stratified, because in a stratified we're sampling people and here we're assigning people, but it has that same feeling of similar groups, and then that's where the assignment or the randomness comes in, is within the groups. All right. The last of these methods we're going to talk about is a matched pair. Matched pair design is actually a subset of block design, but within each block, there are only 2 people. So you can imagine in our class, if I was trying to randomly assign into the CT program, I randomly grab one student and I find this student is Hispanic, male, let's say 18 years old, and I don't know, maybe we have some information about came out of Math 92. And so if I think that your ethnicity, your gender, your age, and the class you had coming into 119 impact whether or not these CT sessions are going to be effective, I might want to control for all 4 of these things, right? So what I'm going to do is I'm going to go back to my rosters and I'm going to try to find another person who's as similar to this as possible. I may not have a really good job of doing this, but I'm going to try. And then I'm going to put one of them into these CT sessions, and the other guy would go into no CT sessions. So that's sort of the idea of this matched pair. There are some subtle ways matched pairs can happen where it's a little less obvious. One is a before and after study. In a before and after study, you act as your own control. So if I gave you a pre-test for statistics, and then we went through the course and I gave you a post-test, I could almost call that a matched pair, right? Where your knowledge before you came into this class was the control, and then after you did the class, that was the treatment. That's one option. You'll see a lot of twin studies as another option if you have a twin. That's a really good, easy pair to do for one of these experiments. So both of those are matched pairs. Like I said, this is by no means a list of all of them. There are other experiments like crossover design. Crossovers when you do one treatment, like you'll do treatment 1 first, and then you'll do treatment 2, and you'll look at your outcomes from both. And a different group will start with treatment 2 and then go to treatment 1, so they can kind of compare and look at the crossover. That particular analysis is a pain in the ass, but it exists. I will note there is one thing I somehow deleted the page from my lecture notes that I made in this semester, kind of defining some of the definitions that go along with experiments, and you do need that for the homework. So I'll probably post one more video where I go through those definitions and do one of the homework questions so that you've got that help there for you. But otherwise, you're definitely good to go and take the JITT for Tuesday, and this is all you need to fill in your lecture notes for Tuesday as well.